Welcome back, everyone, and hello to everyone that's just joining us. I'm Deborah, the founder and CEO of YSYS, and I am your host for today. This is my first time hosting, by the way. So I don't know, if it's anyone's first time being at a hybrid event today. Yes, first time for everything. Awesome. It's also my first time being in front of a Nobel Prize winner. And so I am very, very excited to introduce our next panel with Sir Andre and Timandra. And they're going to be talking about new materials and how carbon atoms are basically advancing telecoms all the way to the healthcare industry. So I'm super excited. If we give them a massive, massive round of applause, and I'll let them take the floor.
Thank you, Deborah. That's good. You see, you're using your skills in topology to escape from. I realise we're now trapped inside our lanyards because of the whole head microphone thing. I just gave up. But that's why, Andre, you are a Nobel Prize winning physicist and I'm not. So I'm Timandra Harkness. I'm not a Nobel Prize winning physicist. My only job is to try and ask some interesting questions and then to invite you to ask some interesting questions. Because you watching the live stream, you do have the opportunity to ask questions. And both of us agreed before the session that questions from the audience are usually the most interesting bit. So get your questions ready in your mind.
Yeah, you have priority. Yeah.
On the stream, you can get your questions in the Q&A or whatever it is, whenever you like, and we will come on to them. So, Sir Andre Geim, Nobel Prize winning physicist at the University of Manchester, Russian, German, Jewish, European, British, Netherlandish, man of the world. I am terribly excited to be here with you. Just to say, the way it's going to work is I'm going to monopolize him for at least 20 minutes.
You should say citizen of nowhere.
Citizen of nowhere. Oh, aren't you a citizen of Britain yet? Surely, since you won the Nobel Prize,
people like me, Theresa May, say citizens of nowhere. I'm proud to be one of them. Yeah,
fair enough. Well, I mean, I'm very excited for many reasons. I don't normally get to sit and chat with a Nobel Prize winner, but I have to say I'm especially excited because I have never ever been with somebody who's won both the Nobel Prize and the Ig Nobel Prize.
And probably will never be.
And you're probably still the only one.
Yeah.
So just actually probably get you to explain what the Ig Nobel Prize is, which obviously is a play on words for the Nobel Prize. It's something like for research that should never have been attempted or something, isn't it? What is the definition of it?
Essentially, you do some work and then put your tongue in cheek, and then people find it funny, and then they ask you whether you are adventurous enough to extend this joke on yourself and accept the Ig Nobel Prize. Unlike the Nobel Prize, not many people dare to accept, but okay, a sense of self-deprecation, okay, can help. So at that time I was just assistant professor, but I decided to accept this. Okay, I have a fig leaf. At that time it was Sir Michael Berry, already Sir and very well-known mathematician at this day. So together we accepted the Ig Nobel Prize, and I don't think we regret it. It was for scientific experiments of levitating frogs with normal magnetic fields. So it's part fun, part real science, and part educational science. So nothing to be ashamed of.
No, well, I was reading the account of it, and if you wouldn't mind, I'd like you to briefly tell the story of how you came to levitate a frog, because it wasn't like you went, how can I entertain the family at Christmas? Let me levitate this frog, was it? It actually arose from pure scientific curiosity. Yeah, so tell me the story.
It was the outcome, Ig Nobel, and this experiment. Essentially, many of you probably heard about so-called magnetic water. So it's a very strange observation that if you put on your tap a small magnet, the claim is that your kettle would no longer be scaled up with this calcination and so on. So the problem with this one, that sometimes it works and most times it doesn't work. And no one knows why, and still it's considered to be quasi-science or irreproducible science, which is essentially the same. So I had at that time in the Netherlands very strong magnetic fields in my disposal. So I decided, okay, if this small magnet works, so what would happen if I put water in a big magnet? And once upon a time, I switched the magnet and poured water inside, and I thought, what would happen to water? It would end up on the floor. Instead of that, I found it levitating essentially in the middle of the magnet. Okay, this kind of facilities and water obviously was available for more than half a century for many labs around the world, and no one has apparently decided to pour water on their very expensive equipment. So I was the first to do that, okay? And I was well educated. I understood after 5 minutes that it's magnetism, so-called diamagnetism, not anti-gravity machine I invented. And my biggest surprise was all my colleagues next morning, no one believed that one. And I demonstrated them, and then colleagues of colleagues wanted to see it. They didn't believe it. And then there was a snowball of people coming out, and eventually I decided it's worth education, if not school children, and then it's probably good for my colleagues who dealt with magnetic field for all their life, from their scientific cradle to their scientific coffin, but didn't know that magnetism can be so strong. So yeah, that's the result. I thought, what can we demonstrate people that all we are magnetic, actually? Yeah, actually, it's repulsive magnetism, frankly speaking, rather than attractive magnetism. So as humans, we're all magnetic. So humans, my face didn't fit inside the magnet, so otherwise I would be there. But a little frog was inside, and then some journalists saw this frog. And you know, when you show something funny to journalists, you as stand-up comedians know what's going on. And then it was out of out of my
I mean, that whole story is great, but there's just a little bit at the beginning that you threw in, that one evening you just decided to pour water into the powerful magnet. I mean, is this an approved way of doing? So you're an assistant professor in the Netherlands at this point. Is this an approved way of doing fundamental research, that you just go, we've got a really expensive, really powerful magnet here. I wonder what happens if I pour water in it?
No. You know, we humans, especially when there are 7 billion humans, or 8 now, on the planet, we try to be competitive. We specialize in very narrow area of expertise, okay? And otherwise you can't be scientist, stand-up comedian, or a journalist at the same time, industrialist, and so on. We specialize. And so in science, which is a microplanet, I think it's about 8 million people who professionally do science these days, and we all have very narrow focus where we can make breakthrough. But and some people normally do it, as I say, from our cradle to scientific coffin, all 40-50 years of our career, hoping to find something unique along the way, digging very deep. But there are people like myself who don't like to dig too deep. At the same time, we try to spread graze around a little bit shallow in the areas where a large herd of elephants didn't eat all the grass, trying to patch and find a small field of fresh grass somewhere. And so this was experiment completely out of my area of research. And most people think that if you do something out of your area of research, you're out of your mind, essentially. But apparently it's not the case. I changed my area of expertise quite a few times, mostly unsuccessfully, but after trying, 1 in well, I don't know, in several cases did bring to some successes, either Ig Nobel or Nobel Prize or something, some publications in glossy journals. So yeah.
I love that. It's like, well, you could win an Ig Nobel or a Nobel Prize, one or the other, or both in this case. No, I think you describe it in your, I read your thing that you had to write for the Nobel Prize. You were saying that it's compulsory and they don't hand over the money unless you,
exactly.
you write your life
They give
story.
you the medal, but not the money unless you write your autobiography and Nobel lecture. It's in the rules of the Nobel Foundation. Yeah.
So if you're studying and feel it's unfair that you have to do your homework, you see, even Nobel Prize winners have to do it to get the money. But I have to say, I bet they're not all as funny as yours, because there were various bits I was reading yours that actually made me laugh out loud. It's definitely recommended reading. You can find it online. But you describe this as, I think, is it Friday night physics, Friday night science?
Yeah, Friday night
experiments.
Yeah,
and you say, I think you did a little back of the envelope sum and said, well, 10% of them have worked out, including your levitating frog, presumably, and including graphene, the thing you won the Nobel for. Is it literally you get to Friday night and before you go home, you just think, I wonder what would happen if? I mean, it feels a bit more than that, actually. It feels like you have a kind of approach to science, which is more almost like a philosophy of, if I'm curious, I should try it.
It's philosophy. Friday night experiment, at least in community of physicists, has become a known phrase. Okay, and it came because I called it at some moments this levitating frog experiment, Friday night experiment. It referred actually to actual events when on Friday night we bought a few beers and share those beers, and after that, you discuss all kind of things. You're a little bit relaxed from your everyday life and you try to do something unusual rather than get bored with your everyday professional experience in this particular area. So people say, I change my subject every 5-7 years. I still change it. It's a little bit all related to graphene these days, but actually very far from graphene these days. I change after the Nobel Prize. I changed it a couple of times already.
Wow! So you didn't stick with your big famous thing. You went, okay, that's done. Before we move on, though, I would like you to tell a little story about how. Would you say you discovered graphene or invented graphene? Which one is it?
With benefit of hindsight, graphene was expected, and theoretically it was known for a long time. But if you ask 99.99 people before that, they would say this material and two-dimensional materials should not exist by fundamental principles. There are very powerful theorems in theoretical physics which essentially forbid this material to exist and similar materials to exist. So for me, it was a discovery, but I think from perspective of the human race, it would be advent of graphene, the proper reference would be, because if someone thought about this, no one used it. We just not shown that the material exists, but that this is a unique class of materials which is out there. Let me, you didn't ask this question, but let me preempt your question. Okay, what is important about these materials? If you look around yourself, everything in our world, whatever you have around you or can imagine, have length, width, and height. You won't find materials around you which are one atom or one molecule thick. And as I said, powerful theorems forbidding completely existence of those materials try to make one atom thick layer of gold, very stable material, it wouldn't be there. It would be completely out of question because, and people knew that thinner materials are less stable than become. So, and we have shown that we have not one graphene material, we have hundreds and thousands of them. So it's a revolution in terms of material science. Not one material, but a whole range, which, 15 years ago, people didn't think it would exist.
That's really impressive. So you kind of happened upon something that then turns out to open a whole new dimension, really, of material science and physics. I was actually going to ask you, you're right, I was going to come on and say, what is so special about it? But I was going to ask you if you could tell us the story of how it came about, because I gather it was really a project you thought up for students to give them something to explore, and then it kind of took off from there.
It's relatively simple and boring story. So I was looking for a new direction to start, and I found out that no one before studied thin films of graphite. Graphite, very popular material, very well studied, but people failed to make thin films of graphite, and presumably there was kind of in literature indications that it would be a simple material. So I decided, why wouldn't we just polish graphite to a very thin layer? We couldn't grow it. All those normal techniques wouldn't allow us to do that. So I gave a student a piece of graphite and try him to polish this graphite. So in a few weeks, the Chinese students came to me and say, "Oh, I succeeded." And I looked at it, and it was kind of too thick to my taste. And so I say, "Try harder," and say, "Can I get another piece of graphite?" He gets this chunk of graphite and essentially polished to the spec. So it was no way to go, but the project was alone. And then we found out that it's another legend, not about Friday night experiment, another legend derived from this research, that legend of the Scotch tape. Essentially what you do these days, actually, people do it routinely in hundreds and actually thousands labs around the world still. They take a piece of graphite, a piece of Scotch tape, and peel a Scotch tape away. And usually people did this for 70 years before us, and they disposed this piece of Scotch tape and studied clean surface of graphite. And that was it. And they throw this Scotch tape into a litter bin, and they didn't know that they throw away their Nobel Prizes as well. So instead of studying this piece of graphite, we looked at the Scotch tape and found out that those pieces of graphite which stick there could be extremely thin, and we pushed and pushed and pushed until we found a single atomic plane of graphite, which is called graphene, which is a layer of carbon which is only one atom thick. And this is not because so unusual that this layer, but then we, after managed to isolate this individual atomic plane of atoms, we pushed further, we start studying its properties, and then it turned out to be gold mine in terms of new physics.
So, I mean, I'm kind of tempted to say you could write a best-selling business book that's just based on this idea that you that people have been throwing away the best bit by just using Scotch tape, and that, you know, what you have to do is look in the litter bin for the discarded Scotch tape of your career, and that's where the ideas are, and then you get the Nobel Prize. Or
it's
whatever.
a little
but that is actually what
this
happens.
is true, actually.
Yeah.
This is actually true. It's with benefit of hindsight, you can present the story like that,
exactly.
but it's the true story.
I think it's a wonderful story. But in a way, I guess it's symptomatic of, if you have that approach of Friday night experiments and let's see what happens, and when you describe the polishing down the block, it does sound a bit like, what we need is a layer of veneer. So we're going to cut down this oak tree and give you the sandpaper. And we want you to keep sanding
This
until you're
was,
left with a twig.
it was ridiculous. Yeah, it was like that. Yeah, but mentality of some people, like, yeah, the boss said something, I need to polish it until all wood is gone.
And then you turn it around, and now you've got graphene, which, as you say, is completely unique in its properties. So you said that they had predicted the existence of something like graphene, but thought it wasn't possible.
No, they didn't predict existence of graphene. It was kind of, because it's so simple material, it's just a chicken wire of carbon atoms, essentially, you can visualize, or kind of a honeycomb of carbon atoms. It was used as theoretical model to describe properties of more complex materials like graphite itself, which is quite a work to do. So it was kind of a toy model for theorists, and there were carbon nanotubes, there were buckyballs at that time, which are also kind of rolled up or wrapped up graphene sheet, but graphene itself kind of presumed to be unstable by 99.99% people, and the rest, okay, maybe 1 per 10,000 people with particularly strong benefit of hindsight. They thought it would be uninteresting to study this material, even it exists. So it's not for isolation of material, because if it would be anything like many other two-dimensional materials, we found a year later that there are plenty of those, okay, a cornucopia of this kind of materials we didn't expect to exist. If it would be just one of those, probably nothing would happen, but the material itself turned out to be really interesting in terms of providing new physics, trying to model some high energy experiments which are impossible in CERN just on your desktop. That's what is Nobel Prize officially for physics, not for anything else.
Well, I was going to ask you that next. That, I mean, it's often talked about as it's this material that's going to transform manufacturing and electronics, and as an innovation tool that can spawn lots of new industries. But you seem to be much more interested in almost the questions that it throws up, the way that it opens doors to things that we don't know, the pure research side. Does it frustrate you that you've discovered this really interesting new bit of science and people constantly want to talk to you about innovation hubs and Manchester as the centre of new industries? Don't want to get you sacked, obviously. But it's just the way you talk about it is much more like, there are these theoretical things, we've got practical things, they throw up new theoretical things. It's much more about physics than engineering.
Humans are societal animals, okay? We have very complex interactions, and we specialize in different areas of expertise. I'm expert in physics, condensed matter physics. It's some people call me encyclopedical knowledge, but it's in the area of physics, and condensed matter physics maybe some other areas as well, but I can't cover, one person can't cover all endeavors of the human race. So I specialize in research. Some people are property developers and industrialists. I can't be both. So I do what I'm doing best, and this is try to find new things about, and industrialization is not my piece of cake. I a little bit participated with different companies, but find it rather frustrating how slowly everything goes. It's not like with graphene like computer program, you write a new app and then, okay, a few years later, you're a multimillionaire or even a billionaire. When you are talking about fundamental physics in materials, it takes 50, 70 years from the beginning. Take, for example, aluminium. No one knew what to do with this material for 70 years. And then airplane industry came around and so on. So with two-dimensional materials, from my perspective, what we have a new range of tools in our toolbox, and we're trying to rearrange those tools to make something new. So at the moment, you probably find around a few hundred different products on the market, consumer market, where graphene is somewhere inside these products, and it's improvement of things, but marginal improvement. It's not like, flip of the switch, completely new out of this. So it's not revolution. Scientifically, two-dimensional materials are a revolution in condensed matter physics and material science, but in terms of industrialization, we have this initial diffusion process of the knowledge acquired in an academic lab into industries. And now this material, 15 years ago, my students sold few micron size. It's smaller than cross-section of your hair, a flake of graphene, something like for £1,000. And people did buy this material because they wanted to study this, they wanted to know this material. They complained that it's very expensive, but my student replied that it's very cheap per carbon atom, because because many of those carbon atoms were there. These days you can buy this graphene in square kilometers if you need, and in tons. The thing is developed, and it's used in many different products. Samsung, for example, what Huawei, they use this material within their mobile phones, paint and other things. Many, but all little applications. Diffusion into the industry rather than revolution in industry so far.
Now, you'll have noticed that I have continued to monopolize, Andre, a bit longer than I said I would, mainly because the iPad went haywire and decided it was going to offer me the Everyman Cinema menu instead of any questions. So hopefully it's off being rehabilitated. But in the meanwhile, people in the room, this is your chance. I think we're back to really old school here. If you've got a question, you put your hand up and, we've got a microphone. Look. Okay,
won't be sharing it around. So if
you won't be sharing it around. Okay.
I'm going to keep it all to myself.
So shout it, and then if I can't hear you, Deborah will repeat your question. Is that hand?
So the question is if there is a foreseeable revolution in foreseeable future, correct? That's the question. Okay, yeah. Depends on definition of foreseeable. I think one big thing, it comes probably not from graphene, but graphene is a shorthand for all those materials which are one atom, one molecule. Say, what is people developing now is semiconductor materials similar to graphene, and graphene kind of too conducting to be used for semiconductor industry. But there are those materials which show very good electronic properties relatively to silicon, which is the base of all our technology. At the moment is a question for academic labs, how to make those pieces not 1 square centimeter, but like this, okay, few inches size. When this people try really hard. Graphene is sorted out. You can make very big pieces, but with those semiconducting materials, it turned out to be much harder. But at the moment, probably the biggest one they can make is is kind of few inches. When it will happen at a decent price, I think this is very silicon industry cannot ignore this, because it's transparent, ultimately thin materials better than amorphous silicon and so on. So that would happen one way or another. This one I strongly believe already for 10 years. I never believed that graphene itself would be a huge interest for semiconductor industry, but those are very interesting materials.
There you go. Anybody else? Okay, you can think about this. I have plenty of questions. Believe me, I could be here all afternoon. I can't, but oh yeah, okay.
You said graphene, it was predicted that it couldn't exist. Could you say like what were into what the physics was
Well, okay. So the question is about why essentially graphene couldn't exist, why people thought that graphene wouldn't exist. The easiest way is to imagine a very thin film of a metal. Take any metal. Let's take gold. Seems to be gold, very stable material. We all know that it doesn't rust and so on. But if you make thinner and thinner film of gold, what you'll find that gold doesn't like to exist as a thin sheet. It coagulates into the droplets. And this is kind of nature of all materials, that when they become very thin, there are so-called phonons. It's essentially vibrations which do not like this two-dimensional order. They try to destroy this order, and coagulation happens this way. You can say differently, okay, simply speaking, okay, materials think, okay, if we have this all three-dimensional space, why do we need to occupy only a part of this? Why don't we occupy all the space? And they all do this one. And to break this law, you have to have a very, very strong bond, which was not actually realized only with benefit of hindsight, having this material graphenes. And when it's such strong bond, like on several of those, many now of those materials, they still can prevent those fluctuations, destroying two-dimensional order, turning 2D into three-dimensional materials.
All right, maybe one or two of the most surprising properties that you didn't foresee that graphene would have because of its two-dimensionality.
It's you can separate the question about what's so unusual about this graphene. And some time ago, about 10 years ago, I put a list of its superlatives. It's kind of the most transparent metal. It's the strongest material per its thickness. It's stronger than diamonds or any other material. It's the most stretchable crystal. It's like a rubber. You can stretch it by 20%. You can't do it with solid states, not polymers, anything else. Most stretchable. It's most conductive material of all. It's actually much more conductive than copper per its thickness. It's or gold. It's the best thermal conductor we know, and the list goes on. That's the first question. The number of superlatives graphene has attracted is about, okay, I can name 15, probably maybe more, depending on the level, how deep in science it is. But in terms of industrial applications, yes, it's a strong material. It's extremely thin, but as I said, it's there is a lot of interplay between, okay, price, quality, what you can do. So with benefit of hindsight, I could probably answer those questions, but we have to live in future. At the moment, really big, not marginal improvement in quality is what I said. It's a semiconductor industry based on two-dimensional materials, which actually, although I got prize for graphene, I think it was unfair because our work was immediately introducing all those 2D materials, which is more revolutions than just one single material.
Graphene getting all the noise. Okay, in the middle there.
Is it the question whether progress is based on better computation or on better experiments? Yeah, there are complex problems which you can't solve without computers, but I think my job is safe as an experimentalist, because in order to use computational facilities and computational skills, you need to ask questions, and those questions are usually asked in experiments. You mentioned protein folding, which is I somehow know about this problem. This is kind of, it has become computational problem, but someone first have done experiments with X-ray and etc. to pose this question. And even when people use this problem, for example, recently we have shown that water doesn't behave in nanoscale the same way as it behaves in macroscopic scale. And those people who do computational experiments on protein folding, they model, they feed up their computers, normally assuming that water has the same properties of the bulk. So you see, you need to ask questions, and computers can't answer all those questions until you make a computer which will be experimentalizing itself.
We are rapidly running out of time. I wanted to just put one last quick question to you. I was reading about your early career and how, despite doing really well at school and college and university with various adverse things, you somehow managed to combine doing really well as a physics student with partying very, very hard, and not doing necessarily all the things you were told. I mean, this has really worked out for you and for science. How does this compare with what your students are like now? I mean, do you have to encourage them to go out and organize post-exam parties? Are they very studious, or are they only too willing to follow in your footsteps in every aspect?
Yeah, partying, yeah. But I graduated from elite university. It was in Russia. You probably all know about how Chinese train their athletes for Olympic Games in those dormitories and very intensive training. So something like that was in Soviet Union, training them to become physicists and so on. Very intensive courses, okay. And in this university, we didn't have as much health and safety, especially, you know, these days we care about mental health of students and staff, and all this infinite number of forms we need to fill inside. At that time, no one cared about this. So you need to find a way to relieve your stress. And I found my way to relieve stress after exam. You one of a sudden realize that it's an interesting subject after it's passed, and then all those questions in your head, how to get rid, to prepare yourself for the next exam, for the next set of questions. So the only way I find, you wash these questions with an alcohol. That's my way. I don't like to advertise this way for everyone, but it worked for me, relieving stress quite well. Okay, yeah. So like a glass of wine after a hard day.
Perfect timing. Thank you very much, Andre Geim. I'm very sorry, streaming people, that we couldn't take your questions. Maybe you can email them in later. Thank you, people in the room, for your questions. And please thank Andre for a great event.
Thank you. Pleasure. Thank you.